All right. Hi, engineering students. It's good to see you again. And I'm coming to you today with a slightly different kind of lesson. Coming to you live from the actual workshop, hold your breath here, in which I'm going to be building the different parts of the projects that are coming up. This is the same place that I also built the aircraft project from the end of last year. And it's my garage. And if you haven't gone and seen it already, these bits of wood that I have here in front of me, this is some red oak hobby board that I got from Home Depot. What you're seeing right here on the table is basically all I have left after building Mrs. Smelly's brand new cart. This is not one of our main projects. It's a little thing I decided to do over the break just to kind of warm up with the whole furniture design thing. And if you haven't seen it, go check it out. She is using it right now. She's delighted with it. It was a replacement for her old metal one that she was using. And you'll see some similarities to Mrs. Jones' design. For one thing, it's got caster wheels. It moves around. For another thing, I really just love the grain on this red oak. It's just like got a really good, interesting grain. This one's not great. It's got lots of little parasite-y things, little borers that have dug in. But other than that, it's beautiful. It sands up well. It stains and takes oil well. It's a very well-dimensioned piece of wood, like very, very sharp and accurate. So I'm thinking of using this for the top of Mrs. Jones' desk just because it looks great, and you'll see that on Mrs. Smelly's one. The other update I want to give to you is that the actuators and the caster wheels for the two projects that we're doing, those should be on campus probably by the time that you have seen this video. So that's cool, and maybe I'll walk around and show you guys how those work, or put them in a video coming up soon. Okay, you should have received your truss kit by now. Here it is. Thanks to Mrs. Peterson for putting these together at the front desk. What you have in here is a little assortment that again was made. It was actually myself and my wife helped make this right here in this exact same garage. And here's what you have. To give you a bit of a softer assignment this week than perhaps last week's one. You have two different kinds of lengths. These are regular old popsicle sticks, as you may have guessed. And I drilled them out using the same drill press that I got as a late birthday present recently that I'm using to build the furniture as well. These longer ones, the ones that are actually, you'll notice they're rounded at both ends. These are 4 inches long. And when I say 4 inches long, I'm actually talking about center to center, not like very end to very end. The critical dimension on truss is the center to center where the pin goes. So these ones are exactly 4 inches. Are they exactly 4 inches? Well, they're as close to it as something can be. There you go, look at that from the very end of my ruler right there. That one's a little shy of 4 inches, but you know, they're pretty close. The shorter ones, here's one right here. You'll notice these ones have been cut at one end and are still rounded at the other. I just, didn't bother to round 200 little things. Can you imagine that? You'll find that these ones are pretty much, well, actually, maybe I'll switch. Here we go. Let's try this. Let's go down to 16ths here. These ones are pretty close to, there you go, there's the 0, 2, and, well, this one's a little long. No, it's a little short, actually. They were supposed to be about 2 and 13/16ths, okay? You can see, counting this way, there's 13 of those 16th marks. There's 16/16ths, obviously, in every inch. This one is about 3 shy of the end. Yeah, like I say, you know what? I didn't do a great job. It was supposed to be 13/16ths. It's actually closer to center, I'd say about 2 and 12/16ths, which is 3/4. In any case, it was pretty close. Those are your two sizes, 4 inches and 2 and 13/16ths. And you might be asking, why would I have chosen a dimension of 13/16? You know, actually, let me just help write some of these things, because, okay, we got 4 inches, and then we had 2 and 13/16. We'll see if my Sharpie holds out for this whole video, huh? So the question is, why? Why 13/16? Well, as it happens, if you take the sine or cosine of 45 degrees times the 4 inches, that approximately gives you the 2 and 13/16. Okay, so what I'm saying is this short one is sine times 45 degrees of the long one. Talking center to center with the holes now. Why is that important? Well, what it means is that these can be constructed. Oops, let me do it correctly. These can be constructed into a 45, 45, 90 triangle. Lining up the holes. Okay. That's how it works. That's how it's designed to work. I did the trig, I did the calculation, I measured them out, I cut them down with a saw, I drilled them out with a drill press in stacks of 10, you'll be glad to know, not individually. There it is. This is a 45, 45, 90 triangle. Look at me getting all fancy here. Oh, that barely worked at all. 45 and 45, and there's the right angle right there. Well, that's cool. So you should have, I think if I remember rightly, I think there were 9 of the larger ones, 9 of these, and 12 of these. Whatever it is, you all have the same amount. And then you have 20 of these little split pins. I remember thinking these were the coolest thing when I was in Sunday school, way back, 30 years ago. Like, I used to think these were awesome. I would hoard them. And then you have a little bit of black twine as well. And we'll get to that soon. So the basic idea is that in this kit, you can make all sorts of different trusses. You can make symmetric trusses, okay, ones which are the same on both sides, like perfectly symmetrical. Those could be for a roof, you know, maybe like arched, like at a roof, leaving space for an attic. Those can be more like a bridge. And when I say bridge, let's talk more about what I mean there. The idea of the bridge one is that you're providing for a flat roadway. Okay, that's the idea of it being a bridge worthy truss or not. Like if I can do that, and then I can do that where I've got like an upper rail and a lower rail. Let's see if this works. I'm not going to pin them right now, but just for, you know, doing this quickly. Like this one here would be an example of a symmetric bridge truss. It would be suitable to make a bridge because I have this lovely flat bottom rail where I could lay a road on, I could lay like train tracks on, anything like that. And hey, if you know what's good for you, you'll have your kit with me as I'm doing this video, and you'll bust it out like I have, and you'll be making this alongside me. All right, this is good for you. Like, get your hands busy doing this. As I said, this week's assignment is going to be a little easier, and it's going to be centered on this kit that you have. So this would be a really good bridge truss. By the way, some bridge trusses, I doubt that I can do this well. No, I can't really. But, you know, wow, that just was a total mess. The bridge truss can also sometimes look like this. Okay, this is completely acceptable. This is called an underslung truss. Okay, an underslung truss is where all of the truss work is underneath. very messy, but you get the idea. All the truss work is underneath, the train would run along the top, or the car runs along the top, and all the stuff is under there, and the supports are right here and here. You don't have to be driving through a bridge with like the truss on either side of you. You can just be going on top of it, and it's underneath you, and you never even see it. That's very normal, very common. You can use these sets to create a roof truss. A roof truss example, I don't know. You might have, let's see here. You might have like let's say a 45-degree angle. What if you had another 45? What if it was like this? I don't know. It's actually not. I won't go into the reasons, but that's not a great truss design. But that would be an example of maybe a roof truss. It is symmetrical. Okay, there's like walls here. You got the roof here, but there's space for an attic. Okay, there's no need for a consistent roadway going across the bottom. So, there is a symmetric roof truss. You can also use this kit to create kind of like the one that we did in the second video last week. Let's see if I can do this. You might have a truss that comes out from a wall. Okay, imagine there's a wall right here. Hey, if you're not enjoying this as you do this along with me, then you might be enrolled in the wrong class. I'm having a great time here. It's fun to make this, it's fun to do it. So there's like one of those ones that's coming out from the wall, and of course that pattern could be extended for as many different pieces as you have in the kit. One thing I'll say, as you make these different truss designs, and I'm hoping that you just kind of play around with it, as you make them, try to not like overdo it. Try to not put too many members, like more members than unnecessary. Like you could really start to, say, bulk this thing out. Like you could put crossbars across all of that, but it's actually not necessary. You've actually you've made what's called a statically indeterminate truss. There's actually more things going on than what the basic equations can handle. So don't go overboard. Keep it to fairly simple triangles in general. I don't think we could solve this one I've just done with the equations that we have. I think you'd get to it and you'd find that you got stuck. I could be wrong, but I think I'm right. So yeah, keep them fairly minimal. Okay, remember that's like the attachment point right there. All right, cool. Let's keep going here. Now, with these little examples that I've done, I haven't bothered to use the pins at all, but I will do that soon, so you can get a feel for that. I'm just sort of showing you some quick design types, but I think you're going to see very, very easily how the pins are going to work. So let's try doing this. Let's try to build an equilateral triangle bridge truss. Forget the short ones for a second. What about just using the long ones? Because they're all the same length, that will create a 60, 60, 60 degree triangle. It's equilateral, which means all sides are equal. It's also equiangular, all angles are equal. Basic geometry here. And let's actually use the pins this time. And you can do this right now. If you can beat me, beat me. We are going to simply feed these little split pins. I made the holes exactly 1/8 of an inch. Yes, I'm a United States citizen now. I am trying to do my best to speak inches and not millimeters. 1/8 of an inch is about, what is that? 3 millimeters, roughly, because there are 25.4 millimeters in every inch. All right, I hope I've given you enough here. Yes, looks like I have. This is going to be a very short truss. By the way, I notice, here, let me point this out. You'll see that some of your members have kind of like a crack there. Sorry, let me hold still. Come on, there we go, camera. See the crack. Don't worry too much about that. If it's a really bad one, we did throw those out. If you've got one still that's got a little crack, it's going to be okay. And if it breaks, you'll probably find you still have enough. Okay, I don't think you can make it any bigger than that. 1, 2, 3, 4, 6, 7, 8, 9. There we go. There are 9 of these. Yeah, you could only... Yeah, no, that's it. That's as long as you can make it with the pieces that I have given you. And I put all my pins in. So you can actually now pick this one up. If you wish, you can go the whole hog. I actually advise using another one. And you can bend the pins back. You don't have to do this, but the pins will certainly unbend back again, and it does just make it a little more holdy togethery, shall we say. There we go. Okay, so equilateral, equiangular bridge truss. Now when I say bridge truss, let me get some props here. I'm gonna build my little supports. Let's see how I go. That one might be a little short. Sorry, I'm just rifling through my wood pile right now. That should do it. Get some clamps. I'm just going to... What I'm doing is I'm kind of making like a little... what would you call it? You know, like the sides of a ravine or something. Let's do that. Do them as far apart as we can. Okay, oops, there we go. All right, that's as far as I can get that one. So let me adjust this. There we go. That feels good. And that's going to sit there. You know, I'm actually going to make them a little further apart with my clamps. Now, if you don't have clamps or a setup, anything like that on your table, you are totally fine. What I advise, just get some big, heavy books. Just put your books right there on the table, and it's going to behave just fine. We're just really trying to get the concepts here. But notice that I've intentionally got my pins just right on the edges of where the valley is. Okay, there's like a raging river or something underneath here, but that is our bridge right there. And this is actually a good time to use the string too. The string, whoops, I've unintentionally tied some knots in my string. Oh, this feels like going fishing with my kids all of a sudden, where I spend most of my time undoing knots. It's still worth being a dad if you can make it happen. All right, let's see. Actually, I would put the string kind of around that. Okay, just kind of tucked it under it there. But then I'm going to flip it over so I can see those studs looking back at me. So this string right now, we have another use for the string later, but right now the string represents the load. Okay, like there's cars driving across, or there's the weight of the thing itself. Either way, we know there's a big gravitational load down. So this represents the load. And so what I can do is I can actually pull down, and using the string allows me to do it very precisely right at this point without like grabbing it with my hands and introducing other kinds of loads which I may not really want, that confuse the issue. And as I pull down here against those books or against those clamped pieces of wood I have, you can just feel like how sturdy and strong it is. This thing doesn't want to give. Even though it's just pins, pins, pins everywhere, there's nothing like sturdy or like steel about it, like a steel ruler. These things in themselves are like, you know, not very strong, but as you pull down on it, you really, really get a sense of just how tough this thing is. In fact, if you're just using heavy books here and here, the books are going to slide before anything happens to the truss. And it really is important that your string is like underneath, as close to the table as possible, If it's not, let's say if you pull it this way and you pull on the string, you'll find your truss just lifts up, and that you just kind of ruin the experiment. So do it down here with the truss as close to with the string as close to ground as possible, and just enjoy the feeling of that really, really tough thing. I suspect that something would snap. Oh, there it goes. It just kind of pops out, but the thing itself doesn't break. None of the members break. Okay, so that's just showing you, like, here's a good little truss simulation. Now I know, and you know, that you could mathematically analyze this. You could say, you know, this load is, let's just make an easy number, 1,000 newtons, 1 kilonewton. You could apply that right there. You would do, you know what I would do? I would label joints like A, B, C, D, E, something like that. Well, actually, let's do this on paper. Let's make this happen. Let's say we had joints A, B, C, D, E. You apply a load right here, and you make it something very easy. No need to do like 2.358 times pi newtons. Just pick something easy, because the principle won't change across the thing. And then you would you'd probably use symmetry and common sense, might I add, to say that there are two equal reaction forces here that balance the 1,000. Okay, adding up to 1,000. Moment analysis works out. I don't even need to know what those distances are. The point is they're all the same, so we're totally fine with that. It's the principle of the shape that matters, not the actual lengths or actual loads. When you do this one here, as we do like little joint free body diagrams one by one, you know, you'd be saying, oh, look at that. There's a force right there. It's got to push down because of the one pushing up. There's nothing else that could push down to resist the upness. But because that's pushing down and to the left, this one is pulling to the right. You would have a similar situation over here. Because this is pushing up, something's got to push down to resist it. Only member CD can do that. But member CD has a rightwards component to it, so we need member ED to counteract that by pulling to the left. Okay, and see, this is a symmetric partner to that. Doing those lets you quickly move around and fill in the other things. Now, please remember, I know this is the most confusing part. When I show these forces, I am not showing what's happening to the members. The members, picture them as kind of invisible to this whole analysis right now. These are free body diagram forces of the joints. The joints are the focus. This is a joint by joint analysis. So I know that, like, say this one here, this one looks like a tension activity is happening to member AB. It looks like these forces are like doing this. Oh, isn't member AB being stretched? No, it is not, because member AB is pushing on joint A. It's pushing on joint B. And if something is pushing back on me, okay, something's pushing back on me, it must be because I'm compressing it. When I compress this thing, I feel it digging into my palms. Kind of hurts because it's being compressed. It's pushing on me because it's being compressed. This is actually Newton's third law. I haven't made that connection yet, but I'm doing it right now. This is Newton's third law. So when you see these forces, that is, the member is pushing on joint A, is pushing on joint B, and if it's pushing back on you, that's because you're trying to compress it. Therefore, this one is absolutely in compression. By the same token, if member AE is pulling to the right on joint A, Well, it's got to be a piece of string. I can't pull on something unless it's acting like a piece of string. Okay? So this is absolutely in tension. Even though the arrows, I get it. These arrows look like they're crushing member AE, but those aren't the forces acting on AE. Those are the forces that AE is creating. Okay? It's the opposite. The focus is on the joints, not the members. So that's tension. By symmetry, we know this is also then compression. This is also then tension. Let's see, over here, I could do a very quick sort of mental analysis here. If 1,000 newtons pulling down, well, something's got to be pulling it back up. So gosh, it's got to be these ones. And due to symmetry, they must be identical. So those ones are pulling up on the joint. Therefore, they're pulling down on joint B and joint C. So this one is also in tension. This one is also in tension. And what's left? Moving around the truss, let's take this one. It's really just this we're trying to solve now. If we do a free body diagram of joint C, I've got something pushing this one here. This one's pushing up and to the left. This one's pulling down and to the left. That's two leftish things happening. I really need something rightish to fight back against it. Okay, and the upness of this one is going to balance out the downness of this one. That's going to work out, but these two are both pointing leftwards, so I need this one to point rightwards. And exactly the same, but opposite over here. How do you like that? How do you like this kind of intuitive analysis, like non-mathematical conceptual analysis of truss? It's kind of cool, actually. And so this is also in compression because remember, BC is pushing on joint B. It is pushing on joint C. It's this situation. Boy, that hurts. Okay, you get that? All right, cool. That is a little conceptual force analysis of a truss. No math was ever done, was ever injured in this process. All right, let me remove my little blocks here. As helpful as they were. And let's try something else. Get rid of my string. We're going to see the string again. Don't worry about that. My string is getting tangled on me off to the side. You can't see that. All right. These are pretty simple. Don't worry too much about, treating them too nicely. We're just really popping them out there. We'll reuse those. By the way, I've done this myself. There are at least like 10 or 12 different good truss combinations that I was able to find just with fooling around. I took a bunch of photos. Okay, let's do one of the like asymmetric ones coming out from the wall. I think I'll just do the kind of one that I had earlier because I likes that one. Actually, okay, here's what I'll do. I'll do the one. It's going to be very much like the one. No, wait, I have an idea. Sorry, I have a plan. Okay. This is going to be very similar to the one that I did in last week's video too, except for the angles. Same sort of like overall geometry, but the angles will be different. They'll be 45 degrees instead of the 30, 60, 90. Okay, you're going to go there. Like any good teacher, I'm kind of thinking in the background, and if I do things and redo things and you're wondering why, it's because I see something that's coming that I'm trying to avoid. You know how it is. I guess you don't know how it is. That's why I'm the teacher. All right, so there's the one. It's a lot like the one from the homework. Quick little picture there for you. Okay, that was in, sorry, I keep saying the homework. That was in the second video of last week. Okay, same thing. But as I say, instead of the 30, 60, 90 triangles, we have 45, 45, 90, 45, 45, 90, 45, 45, 90, and so on. There's the wall would be right here. Now, I wasn't quite sure actually how to do a good wall. Here's my best shot, and I don't know if it's any good, but here's what I was thinking is kind of get a piece of card, and what am I going to use? I need like a pen. Oh, here we go. I've got a little pencil. You know what I have? I have a multimeter with a sharp probe. Look how sharp that is. So I'm gonna use this tool absolutely for what it is not intended for, but it works pretty well, it seems. There you go. Yeah. Okay. All right. And this one. Great. Multimeter away, done its job. This one up here. Remember, you should be doing this. You're not a passive observer. You are a junior engineer. Come on, there we go. Look at that. Glorious. All right, just folded those back to keep them more in place. Cool, cool, cool. Okay, and now you can kind of get a sense. I do have to hold this down. But again, you can kind of get a sense as I pull this down. It is staying in place. If anything, I feel a little wiggling around where the cardboard is, but that's the cardboard's fault, not the truss's fault. The truss is doing a really good job. You could also, if you have some tools and stuff, you could maybe get like I don't know, like I have, little flat sheets of oak wood left over from Mrs. Smelly's cart, or some bits of balsa wood or stuff like that. If you have a drill or something, you could just drill some 1/8 inch holes and you'd be right as rain. Okay, so again, I just want to show you like how to make them, get the idea across. Make sure you're setting these up correctly. Now, I will also say I'm very intentionally doing this whole thing laid flat against a table. Some of you, I think, was it Alan maybe, asked if we were going to do like spaghetti bridges, like man, I can't count the number of schools and classes where I've seen like, yeah, we're engineers, we're going to do a spaghetti bridge. This is cool, and it is kind of cool. And I did those myself as well. But this is called a planar truss, Planar, planar, like a mathematical plane. And the problem with a planar truss is that it's very thin, so it's very unstable. So if you actually do any sort of pulling down on it, as we saw earlier, it tends to actually just flip sideways in an unstable fashion. That's why you'll always, at the very least, see two planar trusses on a bridge on either side with a lot of like webbing and connections in between. That is all just there to keep the thing from flipping in an unstable way. That's an instability which is very real and a very big problem. Okay, that's why I'm leaving these resting on the table, and we're not going to overly stress them to where instability is a huge factor. Okay. Let me show you another little trick here as we do, again, kind of like a soft analysis of this truss, not a rigorous mathematical trigonometric one, which is very important to be able to know how to do, but more of like the soft, touchy-feely kind. I'm going to show you something here. Okay, so we have our truss. I'm just redrawing this. We got pins. Actually, let me do this a little bigger. Sorry, ignore this pin. Okay, what I'm doing here is supposed to be a perfect square with the diagonal going across it. there's the load. We'd be applying load right here. Load P or F or whatever. Like I say, forget that one, just a mistake. I want you to think, when it comes to the whole like tension compression, like what's in tension, what's in compression. Can we get a feel for this? Maybe I'll do this in different color. Here we go. Found a nice little red carpenter's pencil. I'm just going to sharpen it up as I'm talking. What we can do is we can imagine how this thing would deform under load. Okay, how would it deform under load? When I pull down on it like this, Home Depot, this is not product placement, by the way, but if it were, it would be very good. There we go, that's better. How does it deform under load? So imagine like you pull down on this thing. It's pretty obvious that in a very, very exaggerated way, as I were to pull down right here, that we can kind of see as I pull down here, this joint is obviously going to tend to move somewhere downwards. Okay, it's going to try to like displace down to here just under the action of that pulling. What do you think would happen? Let's do some easy ones. What would happen to this pin right here, the one attached to the wall? Well, I guess, you know, we presume it's actually attached pretty well, so it stays right where it is. This one stays right where it is. But these ones are like kind of free out in space. They are able to move and flex. What do you think would happen to this one here? Well, I think it would kind of like split the difference. It's like halfway between here and here. So it would be halfway between staying put and moving all that stretchy way. Like maybe it would go, I don't know, somewhere around here. Definitely not as much as this, but definitely it won't stay fixed like this. This one, yeah, you know, yeah, again, it's probably gonna do a little bit of shifting, but you know, not quite as much. Now, let's connect those back up. Okay. So this is in the red. Let me do this. In the black, we have the original. In the red, we have the deformed truss, or another word for that might be the deflected truss. Now, this is not saying the truss is breaking. It's not a critical problem, anything like that. We're just kind of exaggerating the stretch that's happening across this thing. And like everything stretches, okay? Like all physical objects, when you push and change them and move them, even if they're made of steel or titanium, when you pull and push on things, they always change their shape at a molecular level at the very, very least, at an imperceptible level at the very least. But actually, it's often quite perceptible as well. You know, I can have I have a block of solid wood right here. This, by the way, is walnut. Here's more of that red oak. I'm just kind of messing around here with some little woodworking activities. If I get a really solid clamp, and this is not actually a great clamp, and if I get this and I start clamping it, this block of wood actually gets thinner. Okay, as I clamp and I clamp and I clamp, it really does get thinner. And with this kind of clamp, that would be imperceptible. But if you could get a delicate enough measuring tool, it does get thinner. And by the way, it actually also bulges out. Again, we're talking fractions of a fraction of a millimeter, nothing that you could perceive, but it still is real. So that's what we're talking about here. So we look around these different members, and maybe I should label them. Let me stick with the A, B, C, D, E. Let me stick with the nomenclature of last week. A, B, C, D, E. I think it's pretty obvious that, let's say, DC, is that longer or shorter than it used to be? It's pretty obvious. You can see like this gap. If that had been the same, it might have been the same length, but it's not. That's further down. So I think it's easy to see that this got longer with the flexing. So this must be in tension. It's been stretched. It's getting longer. Again, this one here, clearly that is a longer distance than that original black one. So this must also be in tension. I would say the exact same thing for this. It didn't stay where it was. It moved further down. So this thing had to stretch. That is definitely in tension. Okay, now this is not a foolproof method because as it actually happens, it's a little harder to tell. Man, I could probably do it if I had a ruler, which I do. I don't know why my ruler goes, oh, there it is. Maybe that's easier. This is not really a diagram that you should measure for any kind of real accurate purpose. But you can see there we kind of have like, oh, I don't know, it's a shade past 2.5 inches. This isn't helping my argument. That is still about a shade past. Okay, forget that. But if I really did a good diagram here and it was accurate, we would actually find that one was in compression, this one was in compression, and this one was in compression. Actually, this one does make sense because look at this. That distance. What is that? That's about one. That is about 2.5. And if you come down here, we're definitely at less than 2.5. I don't know if you can see that on the camera, but we're at more like 2 3/8 instead of 2 and about 4 or even 5/8. So that definitely actually got crushed as this thing flexed down. This one, yeah, it's a little harder to tell. Probably I should have actually done this point a little more there because those are supposed to get crushed. But you know, all I'm trying to show is that if you could get access to a good deflection diagram, you could actually tell by the lengthening and shortening whether it was in tension or compression. And a good computer analysis package, of course, does exactly that for you and shows you that kind of thing. And once again, that was the results that we had. Okay, we had compression, compression, compression. Then we had tension, tension, and tension. Okay, the last thing I'm going to do with our time today is also just show you how it is also possible to do something that I mentioned. I don't know if you remember me saying this, but it's very possible to replace the tension members, which we just said were this one, and this one. These three are compression. It's possible to replace the tension members with a tension element, you know, tension structure like a string or a cable. I want you to see this. This is really cool. It almost feels a little unfair, like a little magical, like it shouldn't work, but it does. Watch this. I'm going to take away those members that were in tension. I'm just going to get rid of them. I'm going to get rid of them as solid wooden elements. A wooden element, like any other, like steel or aluminium or carbon fiber, can take either tension or compression, of course. But a piece of string or rope can only take tension. Let me just splay those out again so they won't slip easily. Okay. It's still there. You've just got to imagine it. It's all there. So now I'm going to get my piece of string and let's see what I'll do. All right, you can bear with me. I'm going to show my bestest Boy Scout skills here. Just kidding. I know I've got real This is embarrassing. Now we've got real Boy Scouts in the room, and I apologize in advance. I'm just doing a double granny knot, like my life depends on it. Do you call it a granny knot in this country? That seems like, you know, in 2021, that's probably an offensive term, right? To all the grannies out there. Oh, come on. All right, there we go. I'm just going to kind of loop it around. You could break them off and like tie them individually, but you may as well just make it continuous. The continuousness of it is not what is helping it, by the way. It's the tension aspect which is helping it. Pedro and Sam, this is what you did in middle school. Okay. I apologize for that. I don't know what I was thinking. Okay, check that out. So we've got the same exact truss now. Again, the fact that this is a continuous piece of string has nothing to do with it. If I snipped them with some scissors and tied them all separately, it would be the same thing. I'm just doing this for the sake of speed, and attaching it as well. I can also do the load to give you the full effect, but that's not what's helping it. So what you see is, as I pull down on this, let me grab it right here, let's pull down, I actually get the exact same rigid truss behavior. It doesn't collapse. Oops, my granny knot is about to collapse, but it works just as well. I hope you're doing this at home. I hope you're doing this, because you just got to see it to feel it and believe it. You got to understand this is only working because I picked the exact tension members. If I had picked a compression member, let's say I had replaced this one. I don't have time in this video, but maybe you want to try experimenting. Like, I mean, look, you can imagine it. If you replace this with a piece of string, what do you think is going to happen? The whole thing is going to swing down and collapse and just crumble under you. But in this arrangement, as long as you just truly get the tension members, it doesn't. It's a happy camper. That's it. That's the last magic trick I wanted to show you. Your assignment this week is going to have a lot to do with this kit, so don't throw it away. Treat it well. You're gonna have to take some photos and do some things and answer some questions. But I think it's going to be, as I said, a nice change of pace for you from last week. I hope you enjoyed this lesson coming to you straight from the workshop. I will let you guys be. Hope you have a great rest of your day. Thanks a lot.